Great. Well, we'll go ahead and get started as people continue to file in, but welcome everybody to the October edition, October, of the CDC ATSDR R Users Group meeting. We're very happy to have you all back and have a very exciting guest today presenting on a Shiny app. Before we start, I only had one announcement, just to thank everybody who may be on the call and others who have participated in the survey that we put out. We've sort of used this as a basis for topics that you all might be interested in for upcoming programming. So we're starting to formulate some ideas about that. If you haven't filled out the survey already, there should be an email going out shortly after this. So be on the lookout. We'd love to have your feedback. And yeah, thank you so much. And yeah, I'll hand it over to Sabrina to introduce our guest today.
Hello, everyone. Thank you for joining us for the October meeting. Today, we're really excited to host Lucy DeAugustina McGowan. She's an assistant professor in mathematics and statistics at Wake Forest University. Her research focuses on causal inference, human data interaction, and data science pedagogy. She's very active in the R community. She has a blog that we've shared in the email, Live Free or Dichotomize. She podcasts for the American Journal of Epidemiology's Causal Inference podcast, and she can also be found on Twitter at LucyStats. Today, she's going to be telling us about a Shiny application called ConTESSA, which is used to help quantify contact tracing efficacy. And I will let her introduce that further. And I just want to remind everyone to please hold your questions until the end. We will be ending our session today at 12:15. And so Lucy will open it up for questions. And then just a reminder, if you're calling in from a phone, you can use *6 to unmute. So Lucy, thank you so much for taking time to come and speak with us today. And I'll turn it over to you.
Thanks. I'm excited to be here and to be talking a little bit about this application and then some of the math that kind of went into it. So we made this app called ConTESSA. It's a Shiny app to help quantify contact tracing efficacy. And this is a joint work with the group at Johns Hopkins in their Bloomberg School of Public Health. And so I'm going to kind of talk a little bit about the math that goes into this, and then I'm going to talk about an R package that we wrote that kind of can implement that math that goes into the Shiny application. And then I'm going to show a little bit of Shiny code just to show how we implemented a couple different things that I think are sort of unique in this particular application. And then I'll do a quick demo so you can see how the app works itself. And then we'll open up for questions. So as Sabrina mentioned, I'm on Twitter at LucyStats, and I'm happy to follow up with any of you with questions that you might have about this if we don't have time to address them in the session itself. So you can find these slides if you're interested in following along or looking later. You can find them if you go to lucymcgowan.com/talk. It'll be the very first one listed there. You can get a link to the slides. So that's how you can follow along if you're interested in doing so. So this is joint work, as I mentioned, with folks at Johns Hopkins and the Bloomberg School of Public Health. This is work that I've been doing for the past couple months with Emily Gurley, Justin Lessler, Elizabeth Lee, and Kira Grants. And so that's sort of the team that's been put together to work on both the mathematical modeling, the R package, and the Shiny application. And we actually also have created a Coursera course that is free that goes through this application as well. So if you're interested in kind of learning a lot more than what I'm going to cover today, that is another option. So just a quick outline of where we're going. I'm going to start by talking about the mathematical model, and then I'll go into a little bit of detail about the R package. I'll show you some of the R code to be able to actually run the model. Then I'll get into the Shiny app itself with a couple key aspects and code highlighted there. And then finally, I'll hopefully do a quick demo to show you kind of how it all works. Okay, so the goal of this work, just to give you kind of a big picture of what we're trying to do, is basically test, trace, isolate programs, which are obviously an essential part of the COVID-19 control. They basically offer this targeted approach that many other non-pharmaceutical interventions don't. but being able to sort of evaluate how well they're doing is something that's really important. And so our methodological contributions are in that space, trying to sort of be able to quantify the efficacy of contact tracing programs. And so that gets us into the first section on the model. And so all of the kind of nitty-gritty details on the mathematics behind this are in a preprint that we've got on medRxiv, so you can access that if you're interested in learning more. The title is Maximizing and Evaluating the Impact of Test, Trace, Isolate Programs. And so this is currently under review. So this is basically a mathematical framework for estimating the effective reproductive number given a test, trace, isolate program. And so I think most of you on this call are very familiar with this, but what I mean by effective reproductive number is essentially just the average number of onward transmissions of that an infected individual is expected to make. In this case, and we're sort of saying what's the overall effective reproductive number, and then also trying to quantify what is that effective reproductive number after we've implemented our test, trace, isolate program to be able to sort of look at the reduction between the two. And so we can think of kind of three mutually exclusive compartments of folks with infections. And so we put people into these individual compartments to then be able to sort of help quantify kind of how infections are moving through the community, and also to try to get at this effective reproductive number ultimately. And so the three compartments are the detect compartment, which this compartment contains infections that are detected through testing and subsequently isolated. So this would be folks that just kind of come in from the community that either opt to or are in some kind of surveillance program and get tested and then are isolated. And the next compartment are people who are currently in quarantine. And so this would be people who are in quarantine because they were a known contact of someone who was previously detected. So right now they're in quarantine and then they subsequently become infected themselves. And so these would be infections that are among quarantined contacts of identified cases. And then the final compartment are just infections in the community. So these would be undetected infections. And so the summation of these three compartments would basically make up all infections in your community, and they'd each be mutually exclusive. People would be either in this detect compartment, the quarantine compartment, or the community compartment. And so the first thing that we do with our model is we start with kind of a baseline proportion of infections in each compartment at time t. And it turns out that this kind of first estimation is not kind of the initial estimation is not particularly kind of crucial for where it ends up in the long run, but just to sort of get things started, you can estimate sort of where you think that that folks are when you kind of start looking at your program. So for example, in this example here, I estimate that 20% of the infections are in this detect compartment. So people who are 20% of the infections are, we found out about them because people came in for testing. And then 10% of the infections are quarantined. So 10% of people were in quarantine when they were subsequently infected, of course, and then moved into isolation. And then 70% are just undetected out in the community. So just as a reminder, again, that reproductive number, the average number of onward transmissions that an individual is expected to make, we can assign an effective reproductive number within each of these compartments. For example, the kind of overall reproductive number that we would expect would be the RC, or the community reproductive number. And so this is essentially like without any kind of other mitigation, how we expect that the virus is being transmitted. So that could be estimated somewhere like maybe 2.5, saying that on average we think each infected individual in the community that's going undetected would infect about 2.5 future people. And then meanwhile, in these other compartments, we might have different estimates for these effective reproductive numbers. For example, people who are coming in for testing, we might say that they're only infecting 2 people. And I'm going to show a picture in the next slide that hopefully will help kind of drive home why we would think this would be a little bit lower. But essentially, if someone's coming in for testing and then gets put in isolation, all of that time that they're in isolation, they're in theory no longer transmitting the virus to people. And so you sort of cut off some of those potential future transmissions, and so that effective reproductive number gets lower. And then folks in quarantine, you might imagine that they even have a lower effective reproductive number because they are sort of even more of their transmission time has been cut off because part of that time maybe they were in quarantine and then the rest of it they were in isolation, and so they're much less likely to have onward transmissions. And so those numbers essentially can be pulled from something like this, where this is kind of the theory behind this, which this is a figure from our paper, where in the top, we're looking at cases in generation T. And so it's indexed when the case is infected. And then this is a distribution of infectiousness, or sort of what we would expect for onward transmission. And so this particular case maybe has symptom onset here around day 1, 2, 3, 4. And then they're tested on maybe between days 5 and 6. And then by day 7, they're isolated. And so what that means is that in this red zone, kind of these are potential transmissions that could be happening. But once they're isolated, we're sort of cutting off this transmission. And so this is a reduction in transmission due to isolation. And then the subsequent generation, the infected contacts, we expect that we'll even have further reductions in their transmission because, in theory, when this person was identified as a potential sick individual, their contacts were identified and potentially were put into quarantine, which would shorten this range, but also potentially were isolated even quicker. And so that might reduce the transmission even further for those for the next generation. So we can think of these using kind of that same framework. The R in the community is going to be sort of the static one that is being assumed by the model. And then we can think of the effective reproductive numbers in each of these compartments as being some function of those, where we're basically multiplying those by some gamma. And so that RC is going to be kind of the constant piece, and and these different RD and RQ are going to be sort of functions of that, where that gamma is going to be estimated by using the infectiousness distribution and also some cutoff time. And so here we're integrating from negative infinity up to a TD, where TD is going to be the time from symptom onset to isolation. And then this f of x is just the infectiousness distribution. And so what's happening here is essentially we're only including the time up until they're isolated that they could potentially be transmitting. And then once they're isolated, they're no longer considered to be transmitting anymore. And so this is how this is calculated. And similarly for the quarantined individuals, this will be the time from symptom onset to the quarantine of contacts. And that will be the infectiousness distribution as well, although now it's indexed from the time of symptom onset of the case rather than of the individual who's infected themselves. And so this even shortens the time even more potentially. So that's how those numbers get estimated, kind of behind the scenes in the model. And so what happens is these get put into what we're calling an infection matrix, where they're just on the diagonal of this infection matrix and all the off diagonals are 0. And so this infection matrix, the first row corresponds to the detect compartment, the second corresponds to the quarantine compartment, and the third corresponds to the community compartment. And this infection matrix is going to kind of come into play in a second when we're sort of talking about how this interacts with the initial proportion. And then, of course, we still have to detect new cases as well. So those proportions that I mentioned at the beginning, the 20% in the detect compartment, 10% in the quarantine compartment, and 70% in the community compartment, we can estimate what new infections would come from those by multiplying those proportions times this infection matrix, which just has those R values on the diagonal. And so that's equivalent to just taking those proportions and multiplying them by each of their R values. And so multiplying the first by 2, the second by 1, and the third by 2.5. Okay, so that's how we do infections with this model. And then once we sort of determined who the new infections at the next generation are going to be, we also need to determine what compartments they're going to end up in, so how they're going to be detected. And so for that, we need this detection matrix, which on the rows have the same rows. So the first row corresponds to someone who is infected by someone who was detected. And the second row corresponds to someone who's infected by someone who was in the quarantine compartment. And the third row corresponds to someone who is infected by someone who's in the community compartment. And then the columns correspond to where they end up. So the first column are folks that end up in the detect compartment. And the second column are folks that end up in quarantine. And the third column are folks that end up undetected or end up back in the community. And so this just sort of highlights each of those pieces, for example, infected by someone who is in the detect compartment and then end up being detected themselves. And each of these individual squares are going to be dictated by some probabilities. And so I'm going to sort of walk through a little bit of what that's like. And this is a little bit of an oversimplification. This is definitely how the model works, but when we're doing this in practice, like for example, in the R package I'm going to show, we actually have many more compartments. And so here we just have 3, but in the R package we have 9 just to sort of allow for more flexibility, but I thought it's easier to sort of explain it when we're just thinking about these 3 distinct compartments. So we can write this detection matrix in terms of probabilities. And I'm going to walk through briefly what these individual probabilities mean here. So these omegas here, the omega Ds, this is going to be the probability that a contact of a detected individual is in the detect compartment and is then traced and quarantined. And so, for example, you can see in this middle cell, it's just this omega D is going to be the probability, and that's because that corresponds to the probability of being infected by someone in the detect compartment and then going into quarantine yourself, which is exactly what that describes. If you end up in the detect or the community compartment, you're not put in quarantine, so we end up with a 1 minus that probability in each of those compartments. And so we can estimate that to be something, for example, we could estimate that from our contact tracing program, we might know that 50% of folks who are being detected or being infected by someone in the detect department are then traced and quarantined. And then this omega Q, this is going to be the probability of a contact, that a contact of a detected individual in the quarantine compartment is traced and quarantined. And so again, that omega Q there is going to correspond exactly to that. That's the folks that are infected by someone in quarantine and end up quarantined themselves. And then folks that end up in the detect or the community compartments in the end, they were not quarantined, so you end up with 1 minus that omega value. So we could estimate that to be something like 0.7, which corresponds 1 minus that would be 0.3. And then the final probability here are all of these rows. And so rho is the probability that a community infection is detected and isolated. And so this drives a lot of the kind of overall model here. And so this is basically the estimate of what proportion of infections are you detecting out in the community. And so here, where I'm estimating it's about 20%, so about 20% of infections are being detected. And so all the ones that end up in the detect compartment are being detected. All the ones that end up in the community compartment are not. So they get multiplied by 1 minus that value. And so that's the detection matrix, this the matrix of all of these probabilities put together. And so just as kind of another view of what's going on here, we've got this generation T, the first generation, we have these 3 compartments. And those compartments move through to be, so people are in those compartments and then are infected in this intermediate state. And then those infected folks are then detected at generation T+1, and that sort of indicates where we are as a program. Okay, so the proportion of infections at time T+1, so after the next, kind of at the next stage, is going to be the proportion of infections at time T times that infect matrix times that detect matrix. And so we can plug in those individual values here. And then it's going to be normalized so that we end up having probabilities or proportions that can sum to 1 in these in each of these compartments. And so to normalize it, we just divide by what I'm calling DQC, which is just this vector right here of detect, quarantine, and community times our infect matrix. And so if we divide by the sum of that, we'll normalize this so that it sums to 1. So if I do this math, if I just take these matrices and multiply them by each other and then normalize them, I end up with 18% in the detect compartment, 12% in the quarantine compartment, and 70% in the community compartment at time T+1. And so in order to calculate what the effective reproductive number is at time T+1 based on my test, trace, isolate program, I can multiply this by the infect matrix and then sum it up. And so the effect matrix, those diagonals here, that's going to be that 2, 1, and 2.5 that I had mentioned before. And if I sum all of those up, I end up getting 2.23. So essentially what we said is our contact tracing program is essentially lowering the effective reproductive number of 2.5, which is the kind of baseline number in the community, to 2.23. So that is good. And this is obviously, it's quite sensitive to a couple of these different assumed probabilities, but one that it's especially sensitive to is going to be this proportion that are detected. And so I had previously assumed that the proportion detected was 20%, but just to sort of demonstrate how sensitive and sort of how this model kind of works, if we upped that to 50%, so we said we were detecting 50% of infections in the community, it would change the numbers like this, such that I'd end up with 44% in the detect compartment, 22 in the quarantine compartment, and only 44% left out in the community. And so now this would result in a reduction in R down to 2.1. So we'd end up with an R effective of 2.1. And so essentially what our model is doing is it's letting kind of communities plug in kind of their assumed values for each of these to try to see how well their contact tracing program is doing. Okay, so onto the R package. This package can be installed from CRAN. It's called TTI, or it can be installed from GitHub if you want the development version, also under TTI. It's on the Hopkins IDD GitHub account. And so as I mentioned, we actually have 9 default compartments instead of just the 3 that I had talked about in the kind of mathematical portion, and that's because we just wanted to be able to give a little more granularity to sort of the entire process. And so these compartments are still mutually exclusive. They just allow for 2 extra kind of pieces. The first is that we distinguish between symptomatic and asymptomatic infections, and that's because there's an assumption that asymptomatic folks are maybe a little bit less likely to transmit, and so we want to include that in the actual model. And then we also distinguish between community contacts and household contacts, and that's because we expect that people are more likely to transmit to community or to household contacts than to community contacts. But we also maybe assume that household contacts in a certain contact tracing program are more likely to be quarantined, and so we sort of want to allow for that to be split out. And I should specify here, when I say symptomatic and asymptomatic, what I mean is that like truly asymptomatic, so they never go on to develop symptoms, versus someone who is symptomatic infection. So we have these 9 default compartments, and the main function in our package is this get R effective DF, or get R effective data frame. It has a lot of potential parameters, and I'm going to sort of walk through what those are, but hopefully our documentation is good enough that if you don't sort of remember what I'm saying, you can go through and see it yourself. But essentially, these parameters are going to correspond to those probabilities that I had talked about before, but because now we have 9 compartments, there are several more additional probabilities that go into this. And then we also have some baseline assumptions, things like the reproductive number that's expected in the community, and also the distribution of infectiousness and things like that. So alpha is the probability of an asymptomatic infection. The default I think is 0.2, so we assume maybe 20% of infections are asymptomatic, but you can adjust that to match your community. R is going to be that reproductive number in the community, so that's the RC from the slides that I'd shown before. So this is kind of the baseline reproductive number. Kappa is the relative transmissibility of an asymptomatic individual compared to a symptomatic individual. And so we would likely expect this to be less than 1, since we would think that asymptomatic folks are maybe less, are transmitting less than symptomatic folks. But if you think they're transmitting just as much, you could just set this to 1. Eta is the probability that a contact is a household contact. And so this kind of gets at what proportion of contacts are coming from the household versus the community. And the thing that's going to cause this to toggle are things like policy. So if we're under sort of social distancing or lockdown orders, then maybe people would have proportionally a lot more household contacts than community contacts. And when we're not, maybe it'll be the opposite. Nu is going to be the relative risk of infection for a household contact compared to a community contact. And so kind of how much more likely do we think household contacts are to get sick versus community contacts? And then we have a whole bunch of time parameters, and these all go into sort of getting at that distribution that I had mentioned, where we're going to pick a cutoff time based on when people are isolated or quarantined, and how that plays into sort of that integral where we're sort of cutting off that infectiousness distribution at that point, since we wouldn't expect them to have any onward transmissions from there. And so the T underscore DS, this is going to be the time delay from symptom onset to isolation in a detected symptomatic person. And each of these sort of go on. So for example, T underscore QCS is the time delay from a symptomatic index's cases symptom onset to the quarantine of their community contacts. And so these kind of give a little bit of sense for sort of how quickly are we getting people into either quarantine or isolation once we're detecting that they either were sick themselves or in contact with someone who is sick. And so these would be numbers that hopefully contact tracing programs would have some kind of averages for that they could plug in themselves. And then we've got these omega parameters, and so these correspond to what we had, what I had mentioned in the previous slides. Omega Q is the same, but omega C and H, those are sort of split out from that omega D that I had previously mentioned, where omega C is the probability of being traced and quarantined if you're a community contact, and omega H is the probability of being traced and quarantined if you're a household contact. And so we split those out because maybe there's sort of a higher chance of being quarantined if you live in the same house with someone who has a known positive test versus maybe being out in the community. So these would also be numbers that ideally the health department or whoever's doing the contact tracing would have some estimates for. And then we allow you to work with this quarantine days, the number of days that a contact is told to quarantine. The default is 14, and in the US, I think that's what's happening most places, but abroad, there are a couple places that are working with shorter quarantine times, and so you can sort of shorten that as well. And then row S and row A, so these are the row we had talked about before, which was just the probability of detection and isolation. Now we split it out into whether they're symptomatic or asymptomatic, with the default being that we're a little more likely to detect symptomatic infections than asymptomatic infections, but those can be adjusted based on what you're seeing in your contact tracing program. Okay, this is the last page, and so these all have to do, these first couple have to do with the distribution of infectiousness, and so we've got an offset, which basically is an offset of infectiousness compared to symptom onset. So the default is about 2.31, which is basically just saying that you are infectious kind of 2.3 days before you show symptoms. The shape is going to be the shape of the gamma distribution. So we assume kind of based on general literature that's come out so far that the distribution of infectiousness is gamma distributed with a shape of 1.65 and a rate of 0.5, but you can change that if you think that maybe there's some new research that comes out with different values. And then these last four are if you'd like to do this modeling stochastically. So you can toggle this Stoke parameter to true if you would like to do a stochastic model with overdispersion. And then theta is going to be the overdispersion parameter. And then n underscore inf is going to be the number of infections, and n iter is going to be the number of iterations that you'd like to be run for each unique parameter value. And so these last three would only be populated, they'll be null by default, but you would populate them if you set Stoke equals true. So just to sort of demonstrate how that main function works, we have this get R effective df, and I can set a parameter. For example, if I set alpha equal to 0.3, that's going to say that in my community, I think that about 30% of infections are asymptomatic. And it's going to output this data frame that shows me an R effective, a proportion of cases that are identified, as well as all of the values that are assumed for the other values in this model. And so these are all set at their defaults with the exception of alpha, which I've set myself. And so that 0.3 is corresponding right here in this column. And the kind of main result from this is that R effective. And so under the assumptions that are sort of the defaults plus this 30% asymptomatic assumption, we would see a reduction overall in R of 2.37. And so instead of just running this to one generation, the R function basically runs it to equilibrium, so sort of shows in the kind of long run how we expect your program to do. And you can also include vectors of values. So instead of just having a single value at 0.3, I could look at alpha values of 0, 0.2, and 0.3. And so that will correspond down here. And now I have 3 rows in my output data frame. Because I haven't changed anything else, all of the other values are going to be the same as the default. And that's going to correspond to these new R effective values here. And so those are going to be sort of the way that those are impacted. Those R effective values are impacted both by the fact that this alpha changed, also by kappa, because kappa indicates kind of how much transmission we would expect for folks who are asymptomatic. And then the row S and row A also come into this because row S is basically what proportion of infections we're detecting among symptomatic people, and row A is sort of what we're detecting among asymptomatic people. And then you also can actually have vectors across kind of multiple different parameters if you'd like to change them. So here I'm looking at 2 values of alpha and 2 values of R. And so by default, this is going to create a grid where it'll look at every combination of these different values. And so I end up with this data frame with 4 columns, or 4 rows rather, across every combination of these different parameters that I've input. And I get the corresponding R effective values for those as well. Okay, so onto the Shiny application. You can find all of the code here on GitHub under Hopkins IDD/ConTESSA. And so this is what it looks like when you go to it. ConTESSA stands for Contact Tracing Evaluation and Strategic Support Application. And I'm just going to talk about a couple quick things here code-wise, and then I'll give you a quick demo. And so the first is I'm just going to show you very briefly how to be able to create something that looks like a dashboard. So this is a dashboard in Shiny. And then I'm going to show you how you can include the ability to generate a report in Shiny, because I think that's kind of a nice ability to basically pass parameters from Shiny into a generatable report. And then I'll show you how to save inputs. And so this is sort of in a similar vein, but if you wanted to download the actual inputs that people have put into a Shiny application, that can be a nice feature, because then you can load them if someone wanted to like do some work in the application, download the inputs, and then upload them again. So Shiny is basically, I think most people probably are familiar, but it's a way to be able to sort of build interactive applications in R. And so the kind of main framework for a dashboard, I'm going to use the Shiny package as well as the Shiny dashboard package. And there are kind of 2 components. The first is going to be the user interface, which is defined by this dashboard page function. And you would basically put things you'd like to update in the visuals for the header in this dashboard header function. Pieces that you'd like to update in the sidebar in this dashboard sidebar. And then pieces you'd like to update in the body in the dashboard body. And so you can see exactly what we did. If you go to our GitHub, you can see all of the code that we used for each of those. But just to sort of give this general idea of how you can build a dashboard that sort of looks like one of these dashboards with this sidebar and a nice header and then a body. And then kind of the guts of the function, this happens in the server, so sort of the behind the scenes, this is where our TTI model, our test, trace, isolate model is actually being run, and a lot of the inputs are being processed. And then of course you use the Shiny app function to run the Shiny app. So generating a report, the first thing you're going to do is create a parameterized report as a .rmd file. And this is actually pretty easy to do. You just create your RMD file, your R Markdown file like you would normally, but you can add parameters at the top, and you need to initialize them. So you can initialize them to be missing. For example, here I have 2 parameters, A and B. And then you do something with those parameters kind of in the report itself, and you access them by using the $sign to access this list of parameters. And so you do the params $A to access parameter A, for example, or params $B to access parameter B. And the reason this is neat is because you can use this format and you can pass parameters from your Shiny application, so from what users input in your Shiny application, to a static R Markdown report that you could then turn into like a PDF or a Word document that someone could take home with them or print or something like that if they'd like. So that's these parameters here and what's being printed here get pushed from the Shiny app itself. And so the way this works is first you have to update in the server function. You would add this download handler function, and you're going to output it to something in the output list. For example, here I call it report. And so I take that report.rmd that I just created that has those empty parameters as well as the code that references the parameters. And then I create a list of parameters from my Shiny application, and this can contain anything that is in your server function. So you can contain inputs, which would be direct inputs that the user inputs themselves, or you could put kind of manipulated variables that you may have calculated as part of your Shiny application. You can put reactive variables in there. You can put basically anything that's being run within the server side. And then you just use the R Markdown render function. You specify the parameters down here so that you actually specify that you'd like those parameters to be passed to that Markdown document, and it'll render it as a PDF or a Word document or whatever you specify. And then the UI, it's pretty easy. Just in the sidebar, you're going to stick a download button so that the user can actually download that. And you're going to make sure that you put the same name that you used for the output here. So I called this output $report. And so I want to reference that I'd like for them to download the report. And that's it. The next piece I thought I'd mention is the save inputs. And so for this is basically the way that you save inputs on the server side. Again, we're going to use a download handler for this. And the way you do this is essentially you can use this reactive values to list, and you can pull all of the input values. And so this is going to be everything that the user inputs. And then once it's a list, you can basically do whatever you'd like with it. For example, I put it into a .yaml file for users to download, but you could put it into a text file or basically anything that you would like to then upload later if you'd like to let users sort of re-find their space. If they've entered a whole bunch of data and then want to come back later, this is a nice way to do that. Okay, so I've got just like a couple minutes. I'm going to very briefly show you a demo. I want to mention again, we've got this Coursera class that's free that sort of goes into much more than what I'll show in this demo. But to get to this link, we're going to go to this IDD Dynamics at shinyapps.io. So I'm going to go there now. Let's see. Okay, so go to IDD Dynamics, jhu.shinyapps.io/ConTESSA. And so I'm just going to very briefly walk through kind of how I would use this application. I'm going to skip a couple things just so that we can do it quickly, but the first page asks for your community name and who's preparing the report. So I'm going to say I live in the Shire and my name's Lucy. These are optional. It's just so that if you generate a report, it sort of includes information that's relevant. And so this first page is focusing on surveillance and isolation. And so this is going to have questions about sort of the detect compartment. And so the first question is asking about, on average, what's the average number of cases that's detected? We have these little hovers that you can click on if there's anything confusing here. And so I'm going to say that we're detecting 7,500 infections on average per week. And then the second question is trying to get at the denominator. So what are the total infections in your community so that we can calculate what % of infections you're detecting. And so you can do that two ways. You can either get help with the calculation by using the infection fatality rate to estimate it, or you can try to estimate it directly. So if you do it the first way, you'll estimate the average number of COVID-19 deaths in your community, as well as the infection fatality ratio that you think best represents your community. So if you had maybe an older, sicker community, you might pick a higher number. If you had kind of a younger, healthier community, you might pick a lower number. Or you could just estimate it directly, like if you did some seroprevalence survey that made you think that you were detecting 30% of infections, you could move it up to that. And then this next question asks about the average number of weekly cases that are isolated. So there's potential that maybe not everybody that's being detected is being isolated, although in my community, everyone is being isolated. So I'm going to put this up to 7,500 to match, to match the actual number. And you'll see you get errors if you try to say more people are isolated than detected, since that doesn't actually make sense. And then also we ask about what number of newly isolated cases there are, because we don't want to include people who are detected in quarantine, since that's sort of a separate compartment. And then these last two questions have to do with timing. And so these are getting at those T values from the R package. And essentially the first question is just asking about the time from symptom onset to getting a test. So this doesn't actually play into the model, but just sort of helps frame what people are thinking about, because I think a lot of health departments are thinking about the time from symptom onset to testing, and then the time from the test date to when we're getting people isolated. So basically, how quickly are they getting their test results back and then going into isolation? And so I'm going to say in my community, on average, we're doing really well. People are getting isolated within 3 days of symptom onset on average. And then this next page, if I click next, and I can either be navigating on the bottom through those next, or I can navigate via this sidebar. The same thing will happen. And so the first question asks about what's the average number of household contacts per case. The next asks about, this is that omega H. This is among cases detected in the past 4 weeks, what % of their household contacts are traced and quarantined. So I'm going to say 70%. I'm going to say we're doing a good job. And then this is getting at the time from symptom onset of a case to quarantine of their contacts. And so I said that my cases are getting identified and isolated within 3 days. And then I'm going to say that their contacts are on average getting isolated or getting quarantined 2 days later, so within 5 days. And then this page is an exact copy, but just for community contact tracing. And so once you've done that, you can see this dashboard that then will show you the reduction in R. So the R by default is assumed to be 2.5 in the community, although in the advanced options you can change that. And based on what I input into these 3 kind of data input sections, I see that my contact tracing program is reducing that R effective down to 2. And that we're isolating or quarantining about 43.9% of infections in my community. And so we also have these graphs that kind of let you see how you would do if you were to change any of these parameters. So for example, if we were to detect and isolate a larger number of folks, kind of how that would reduce R. And so if we wanted to get our effective reproductive number all the way down to 1 just from contact tracing, so not from any of the other mitigation strategies, we could do so by isolating and detecting about 88% of cases. And we also have plots that show kind of how responsiveness or how timing to isolation changes those numbers. And then there's a tab that shows the changes if you look at the community or the household contact numbers as well. We also have the ability to create a scenario B, where basically you can create another scenario that looks at sort of a different setting. Maybe you're not quite sure about some of these values, so you could change a couple of them and generate a scenario B that will then get plotted that you can compare to. And so you can compare your scenario B to your scenario A to kind of see where you land there. Okay, so that's what I have. I will turn it over now to questions if people have them. And yeah, thank you so much. This has been such a joy.